In this video, we are going over section 10.3, which is about performing a hypothesis test about a population mean. So in 10.2, we did a hypothesis test about the population proportion, and these are going to be very, very similar. As we go through this video, it's really going to feel like deja vu. We're going to work another example. Go through all the steps and try to explain as we go. But since this video is so similar to the previous one, I might be working through this a little bit more quickly and instead emphasizing the differences. So I don't want to waste your time. And starting off this video, I assume that you've already watched and fully understood what was going on in section 10.2. So it helps to develop our little, mental structure of what's going on in this course a little bit. And so what I want to point out to you is that we've been developing side by side our statistical methods for both proportions and means at the same time. So in chapter 8, we were talking about the distribution of the sample proportion and the distribution of the sample mean. And there were two different sections in chapter 8 that dealt with each of these. In chapter 9, we were talking about building confidence intervals for proportions and means. In chapter 10, we're talking about hypothesis testing for proportions and means. And in chapter 11, we'll be talking about how to build a hypothesis test for a population proportion, let me try that again. In chapter 11, we'll be learning how to build a hypothesis test for two sample proportions and how to build a hypothesis test about two population means. Of course, there's two different cases for the population mean. Either these are dependent or independent sampling methods. So there's two different sections for that in your textbook. But again, what we're doing right now in this video is hypothesis test about the population mean in 10.3. So again, you've seen this before. What we're doing in this video is we're going to investigate what kind of math do you need to determine whether your data set represents sufficient evidence to conclude in favor of an alternative hypothesis. And this time we're talking about a hypothesis test about a population mean. So here's an example. I make a claim, and the claim is that the average height of an emperor penguin is greater than 47 inches. So the way I write this is I say, well, my claim is my alternative hypothesis. So my alternative hypothesis is going to be that this average, this population mean, is greater than, well, it's some mu naught, where I'm saying that mu naught is going to be 47 inches. And then my null hypothesis is just going to be the converse. It's going to be that mu is less than or equal to mu naught. Hopefully that checks out. And in doing so, kind of what I was thinking in my head was, first, what are we seeking evidence for? That was my alternative hypothesis. And then second, what was the converse of that? And that was how I wrote my null hypothesis. So again, here they are, my two hypotheses that I need for my hypothesis test. We're going to gather data by, let's say, measuring the height of 20 penguins. So that means n is equal to 20. And after I take those measurements, maybe I calculate a sample mean of 48.6 and a sample standard deviation of 2.8. Now, our goal is to calculate the probability that if the null hypothesis is actually true, we could obtain data like ours or more extreme than ours, right? So, in other words, given that my null hypothesis is true, or given that really the underlying population proportion is exactly 47, Remember, 47 is what I'm calling my mu naught. That's the boundary between the null hypothesis and the alternative hypothesis. Given that this is true, what's the probability that I could get a sample of 20 random measurements that gives me a calculated sample mean greater than or equal to 48.6, which is the value that we calculated from our sample? We're going to call this the p-value when we find that probability, and the steps to calculating the p-value look like this. Well, there's an extra slide in here that just says whenever we calculate this p-value, we're going to compare that to the level of significance, which we use the Greek letter alpha to represent level of significance. And if my p-value is less than alpha, then we can reject the null hypothesis, but if my p-value is greater than alpha, then we do not reject the null hypothesis. Okay, so you're going to choose the level of significance. Just like before, if it's okay to have a type 1 error, then you can make A larger. Making A larger will is actually going to improve or increase the power of the hypothesis test, and we talked about how that was good in section 10.1, but also making A larger increases the chance of a type 1 error. If it's really bad to have a type 1 error, then you want to decrease the chance of having a type 1 error, but this is actually going to decrease the power of your hypothesis test. And so there's a trade-off here. I didn't emphasize this enough in the previous video, but choosing your level of significance introduces a trade-off. Either you're going to have a high power of your hypothesis test and a high chance of probability of making type 1 error, or you're going to have a small probability of making a type 1 error, which is a good thing, but you're going to have decreased power, which is also a bad thing. So you've got to choose alpha to really optimize this trade-off. And that's going to vary. I mean, that's not going to be the same for every application, but for our typical use, we're going to use an alpha of 0.05, which we talked about before corresponds to about 95% confidence, 95% minimum confidence. And for other applications, maybe alpha is larger, maybe alpha is much smaller. And a lot of this is like before, so we'll try to keep moving. Just a quick reminder, if you do not reject the null hypothesis, that means you did not find enough evidence in favor of your alternative hypothesis. If you do reject the null hypothesis, this is saying that we did find enough evidence in favor of our alternative hypothesis. So how do we calculate that p-value? Everything here hinges on calculating the p-value and comparing it to my level of significance. So how do we actually calculate this p-value? First, we calculate the standard error of the mean. So remember, this is the standard deviation of the distribution of my sample mean, or at least this is our best estimate. This is our statistic that estimates that parameter. In any case, this is just the underlying standard deviation, which we can calculate from our sample, divided by the square root of the sample size. Now, in our example, I gave you a value for S, and I told you that our sample size was, I think, 20. Let's go back to our example. Yeah, S was 2.8, X bar was 48.6, N was 20. Just scroll back up because I have such a bad short-term memory I can never correctly copy these numbers. So 48.6, 2.8. Okay, excellent. So then let's calculate this. Let's calculate lowercase s subscript x bar. That's going to be 2.8 divided by square root of 20. So here's 2.8 divided by square root 20. And that is 0.626. Oops, 626, I think I said. Okay. Next, we're going to compute a test statistic. And unlike last video when we were using lowercase z naught for the test statistic for the proportion, we're going to use lowercase t naught to be our test statistic for the mean. Okay, so down here in the denominator, that value is 0.626. This x bar is going to be 48.6. And my mu naught, which was the cutoff for my hypothesis, well, that was 47. So plugging all these in, 48.6 minus 47 would be 1.6 in my numerator, divided by 0.626. And so this value t naught is going to be something a little bit larger than 2. .56. So I've calculated my test statistic, and then just like in the last video, we have 3 different cases. Either this is a right-tailed test where I'm hypothesizing that my mean is greater than a certain value. It's a left-tailed test, because maybe I'm hypothesizing that my mean is less than a certain value. Or maybe it's a two-tailed test, because I'm just hypothesizing that my mean is just not equal to a certain value. So in these 3 cases, we have different formulas for my p-value. Remember, now, since I'm using a test statistic that looks like lowercase t naught, this CDF is referring to the CDF of the t distribution. So just be aware, this is the t distribution CDF in all 3 of these formulas. And the t distribution is always going to ask us what our degrees of freedom is. Well, this will be n minus 1, which is 20 minus 1 in our example. So our degrees of freedom for my example is going to be 19. And also from the previous page, t naught was equal to 2.56. Now, what kind of hypothesis test are we doing? Well, I'm hypothesizing, I think, that the height of the emperor penguin is what? My alternative hypothesis is that the average height is taller than 47 inches. And so this is going to be a right-tailed hypothesis test. So my p-value is going to be 1 minus the CDF evaluated at 2.56. So in my calculator, I do 1 minus the second VARS. Now I want the t distribution CDF, so that's going to be number 6 on this list, with 2.56 as my t naught. My degrees of freedom was 20 minus 1, or 19, and then I paste, and that is going to give me a value of 0.00957. I mentioned this in the previous video, but since the t distribution is symmetric, rather than doing 1 minus the CDF of t naught, another thing you could do is you could simply take the t distribution CDF, and instead of putting in 2.56, we could put in negative 2.56, and it would give us the same answer. Again, if that's confusing to you, leave it alone. Don't worry about it. But anyways, the value we're getting back represents my p-value, and that's going to be 0.00957. That's a very small p-value, and so if you remember the last video well, maybe you're thinking to yourself already, this is going to result in a high confidence in my alternative hypothesis. Because 1 minus the p-value, so 1 minus 0.00957 times 100%, that's going to represent my percent confidence I have in my hypothesis. So 1 minus that p-value is going to be 99%. I have 99% confidence in my alternative hypothesis. In other words, that means there's only really like a 1% probability that I would be committing a type 1 error by rejecting the null hypothesis. And so I would actually feel pretty confident, telling people about my alternative hypothesis or concluding in favor of my alternative hypothesis because there's only a 1% chance that I would be wrong. That's why I say I have 99% confidence. And I said this before, I'll say it again. I just think it's so cool that there's math out there that allows us to assign an exact percentage to the level of confidence we have in a given claim. Right? So this percent confidence, when I say I'm 99% confidence, I'm not just telling you about the way that I feel, but I'm actually telling you about a probability that I'm wrong. When I say 99% confidence, I'm saying there's a 1% chance that I'm wrong about my alternative hypothesis. So, like I mentioned in the previous video, we can make a hypothesis test using a confidence interval as well. And so the idea is you would construct your confidence interval about the population mean first, the way that we did in section 9.2. I won't go over that again because there's already a video about section 9.2. And then we ask the question, does mu naught fall within the confidence interval? If it does, then we would not reject the null hypothesis. But if mu naught falls outside of the confidence interval, then we may reject our null hypothesis. Again, the benefit of doing a hypothesis test using a confidence interval is that you can, accept or reject your null hypothesis, and you already have a confidence interval made. But without calculating the p-value, you won't have an exact percent confidence. So the benefit in doing the p-value method is that you can accept or reject your null hypothesis, and then you also have an exact percent confidence you have in your alternative hypothesis. So there's pros and cons to doing both. And if it were me as a statistician evaluating some claim, I would actually do my hypothesis test using both methods. Number one, to check my work and make sure that I accept or reject the null hypothesis the same way in both methods, right? Because I can't have those disagree. And then for two, that way I would have both my p-value, my confidence, and a confidence interval, because both of those are nice to know. Okay, I didn't include a slide, but the last thing I'll point out here is that there is a shortcut on your TI-84 for performing this type of hypothesis test. So we're going to go to second, no, not second. We're going to click the stat button. We're going to go right over to tests. This time, we're dealing with a t-test. I think it's number 2. So it's a t-test because I'm using the t-distribution CDF here to evaluate my hypothesis test. So don't forget, when we're talking about the mean, then we're talking about the t-distribution. We're talking about the proportion, we use the standard normal distribution, but in our case, with the mean, we use the t-distribution. Don't forget that. I'm going to input stats this time, because I don't have actually a data set. My mu naught was 47. My x bar was 48.6 from my example. My sample standard deviation we calculated, let me try to find that. That was 2.8. And the n value, my sample size, was 20. What type are we doing? Well, we were doing a right-tailed test because my alternative hypothesis was that the average height was greater than 47, so I select the one that says greater than mu naught. And then, like I said before, the calculate button doesn't really tell me a whole lot more than the draw button does, and so let me just click the draw button. And here, the calculator is drawing a t-distribution, and just a little bit it highlights in blue over here that area under the curve highlighted in blue represents my p-value. Remember, that's the probability of making a type 1 error. And you can see it's so tiny out there to the right. It's only 0.0097. And that's exactly the p-value that we calculated. And the other thing is that it gives me my t-test statistic, which is 2.56. That's exactly what we calculated for our t-naught test statistic. And again, the unshaded region underneath this curve would represent my percent confidence in my alternative hypothesis. So since the majority of the area under the curve is unshaded, that tells you that I have a very, very high percent confidence in my alternative hypothesis. Okay. Thanks, and have a great weekend. Best of luck. If you have questions, of course, send me an email or a Canvas message, and good luck on your homeworks.